Okay, so we'll just go ahead and get started. I might not have enough material to fill a whole hour and a half anyway, because I only have 4 pages of notes. Wait, what?
Carly's here coming.
Oh, okay. Well. Oh, okay.
I showed my students my notes today for Monday because they were complaining about writing.
What?
My students were complaining about writing today, so I come over and I took my Monday's notes out of my book and showed them. I said, "Look, I don't want you to complain about writing.
Okay.
Trust me." And then one of them started reading it, and he said, "What language is this?"
That's the best response.
Mm-hmm. Yeah.
Because I mean, my kids complain about how long a homework problem is because it takes like 3 lines, and I'm like, "Boo, try 10 pages." Like, here, that was modern algebra.
My buddy was complaining. One of my best friends was asking how it was. And I said, "Is it hard?" And I showed him a sheet. He said, "I can understand about 2 words on there. That's it."
Well, I remember, I think it was Cal 4, and one of us complaining about a certain problem taking 25 minutes. And like, it might have been a whole assignment. It was, yeah, it's like, I remember
Is this my class?
spending, what? No, later. Spending several hours on one problem, even as an undergrad.
Modern? Yeah.
No, not a modern, but
Well, no, for me, like
oh
modern.
yeah, yes,
we work
modern,
like
but even
groups of 8.
yeah.
And we'd have 10 questions, and it would take us 72 hours
Mhm.
with 8 brains to get 10 questions.
Yeah, so that's the problem. Is students are getting wussier by the year. So, but I guess we let them. No. Okay, so now that everybody who could possibly be here is here, and hope you haven't missed anything. So I was just barely starting. Today we wrap up chapter 6 on eigenvalues by talking about singular values and singular vectors and how we compute those using ideas from computing eigenvalues. And then what I have very vaguely planned for the rest of the class is some introductory material about machine learning. And I have had 0 opportunity to prepare anything for that, but I have Easter. So I'll have basically a week to be ready for that. We'll just have 3 class periods of that, and then it's all over. I may not be able to. I think what I will do, since there won't really be time, since you guys are still finishing up the chapter 5 homework, still waiting for most of you to turn that in. Hopefully that's coming soon. Because I'm really dying to ruin my Easter by grading it. So, that'd be the best Easter basket y'all could give me. Yes, I'm kidding. So, I guess I can regret saying this, but you guys waiting until after Easter would be the best Easter basket. But the point is, then there's some time for chapter 6 homework, and then we kind of run out of semester.
Yeah.
So what I will, but even though you guys are all graduate students, I know that if I don't assign something related to the last material in machine learning, then you guys will probably just like not show up or not paying attention or pay less attention because.
We'll be very engaged. You should just give us a quiz on that.
Well, that already, and don't blame Teresa. I'd already thought of it doing it anyway.
Well, I mean, I would rather a quiz than a homework assignment.
Well, yeah, that's what I'm going to do.
Oh, okay.
Yeah, so
yeah.
but yeah, I did get in my head before you mentioned it, so it's my fault, not hers.
So stop stealing ideas, Teresa. Stop stealing ideas.
I'm so sorry that I gave us all homework.
Yeah.
Never. It's physically impossible.
Your voice will reverberate in my class even after you've graduated.
Boy, I hope so. Randomly FaceTime you. It's Newton.
Okay, so I get to spend today describing my advisor's crowning achievement of his career. computing the singular value decomposition. And he developed it the year I was born, 50 years ago. And let's see, how old was he back? He was 37 at the time. So, although I guess my crowning achievement KSS methods were created at a slightly earlier age, but they just don't have a notoriety that this does. But I'm still working on them. So, to refresh your memory about the SVD, we saw it some time ago, but it's been a while, a couple weeks. The singular value decomposition of any n by n matrix A is this U sigma V transpose, and U is, I'll try to size it below. U is m by m, V is n by n, and sigma is m by n, same size as A. Also, U is orthogonal, V is also orthogonal, and sigma is diagonal, has the singular values on a diagonal. So they're all real numbers, non-negative, always ordered, sigma 1 being the largest, and so on. And so when we saw this earlier, it has various applications like low-rank approximations, solutions to certain least squares problems, and so forth. So, and those are only a few of the applications. There are quite a few more that I didn't get into. So only now, having covered algorithms for computing eigenvalues, can I finally describe how do we actually compute the SVD. And since there isn't actually a whole lot of material here, at least I can go into some details, and you can see some fundamental operations at work, and I can focus on those too. Because what I'm going to do is I'm going to reduce the problem of computing the SVD to an eigenvalue problem. So, the thing is, as an undergrad, I never heard of the SVD. It just wasn't covered in any linear algebra class I'd taken, which was kind of strange. Although I'd not taken a class like this as an undergrad. But when it comes to Stanford, where the creator of the SVD algorithm was, his license plate was Dr. SVD. And then when he traded in for an SUV, it was Prof. SVD. And I'm thinking, you know what, maybe I should get my own vanity plate, because I've created KSS methods, and do that. But I have two problems with that. One is I have a very uncool car that has no business having a vanity plate on it. So
It is very gas friendly.
Yay. So I spend a little on gas because I commute 5 miles a day. Yeah, so that's one problem. And the other is that people around town see me driving around with Dr. KSS or Prof. KSS. I don't think Mississippi would allow Prof. to be doctor. And they'll think it's short for KISS or something, and they'll get the totally wrong idea. So I'm not sure what I want to do, because I'm dying to blow my full professor raise on a cool car. But because my full professor raise will be about the size of a typical car payment. So we'll see how to wrestle with that later. No, I used to own 2 Pontiac Grand Prix. And one license plate was Dr. J, and the other was Dr. J2, because it was the sequel. And I was living in California, so what do you expect? But we didn't make the journey here. So starting with, how am I going to reduce this to an eigenvalue problem, something that we know how to solve? So if I start with A is U sigma B transpose, and I'm going to rearrange this. So it's kind of like doing ordinary algebra, just keep in mind we're working with matrices. If I multiply both sides on the right by V, V is orthogonal. So V transpose and V cancel out, so I have A V equals U sigma. Now, sigma is a diagonal matrix. So this is just one of those good to know things because it comes up fairly often when manipulating matrices. When you multiply a matrix on the right by a diagonal matrix, that has the effect of scaling the columns of this matrix on the left. So in other words, the first column is scaled by the first diagonal entry. The second column is scaled by the second diagonal entry, and so on. So to write that out on a column by column basis, so I have A times V1, V2, Vn on the left side, and then on the right side, I have U1, U2, Um, and then diagonal matrix, sigma 1, sigma 2. Now, M and N are not necessarily the same, and we don't even have any assumptions on M or N being, like one being greater than the other. But I'm going to have here sigma P, where P is the minimum of M and N, because that's how many diagonal entries you can possibly have, one way or the other. Also, P is greater than or equal to R, which is the rank of A. And we saw from a homework problem you had, from a chapter 4 homework, that R is the number of non-zero singular values that you have. So one thing that I can, so if I look at this on a column by column basis, then I have for a first column, A V1 is equal to the first column of this matrix, which is U1 times sigma 1. But sigma 1 is a scalar, so I can move that wherever I want. And I can keep going. So in general, I have A Vj is equal to sigma j uj for j equals 1, 2, up to p. So at least up to the minimum of m and n, this relationship holds. Now, there's one thing I can say is both sides of this equation, what you have is a m by n matrix. So you're going to have n columns altogether. So what would happen in this case is, let's suppose that m is less than n. Then I'd run out of columns. But all that means is, in other words, I'd run out of columns from u, but I'm going to still have n columns altogether. It just means the excess columns are 0 in that situation.
What is P? You said P equals what?
Oh, P is the minimum of m and n. Yeah. Because you have n columns of V, you have n V's, m U's. For this relationship to hold, you got to take the minimum for this to even make sense. So if n is strictly greater than m, then I have avj is equal to 0 for j equal m plus 1 up to n. So that's how you handle the case of the dimensions being different. So if A is not a square matrix. It's better still be recording. Yes, it is. Okay. All right. So we have this relationship between the right singular vectors and the left singular vectors, just by looking at this column by column. Now, I could do the same thing by looking at the transpose. If I take a transpose of both sides of this equation, A transpose equals V sigma transpose U transpose, and I can multiply both sides on the right by U, so A transpose U is equal to V sigma transpose, and then I get column by column, A transpose Uj is sigma j Vj. From j going from 1 to p again. If m is strictly greater than n, then A transpose times the other u's would be 0. Now, I can really work with either relationship that I have here, but I'm just going to work with this one. So AVJ is sigma j uj. Well, you know what? I actually need both of these for what I'm going to do next. Right, so I haven't wasted too much time. So now what I can do is put the two relationships together. So if I start with AVJ is sigma j uj, and I'm going to assume j is between 1 and p, just for simplicity. Then I'm going to multiply both sides on the left by A transpose. And I think it's because sigma j is a scalar, I'm allowed to move that. It's the only, so all of those things keep in mind that you gotta respect the order when it comes to matrices, but constants you can put wherever you feel like. And usually it's best to put them out front. Now I can apply the second relationship to A transpose Uj, because that is A transpose Uj is sigma j Vj. So now I have this relationship. A transpose A Vj is sigma j squared Vj. So this is the key right here. What does that tell us about, well, what can we say about Vj from this equation? We've seen this kind of equation before. Matrix times a vector is scalar times the same vector. No. What can we say about Vj? What kind of vector can we call it? What?
Is it a unit vector?
Oh, actually Vj is a unit vector, but that's because of the form of the SVD, not because of this. Okay, matrix times vector. Yes. Vj is an eigenvector of A transpose A. So, eigenvector of A transpose A. All right. So again, it's important to cultivate this into a reflex. Matrix times vector equals scalar times same vector. That's an eigenvector. The scalar involved is an eigenvalue. The eigenvalue sigma j squared. Now, if I were to apply these two relationships, this one and this one, in the opposite order, and we will need this here just for completeness. We have A transpose Uj is sigma j squared Uj. So Uj is an eigenvector of A transpose. So we just put the matrices in the opposite order. And the same eigenvalue, sigma j squared. So the squares of the singular values are eigenvalues of some matrix. And not only that, symmetric matrix. A transpose or A transpose A or A transpose are symmetric. Now, we know we have a way of computing the eigenvalues of a symmetric matrix. It's a symmetric QR algorithm. So, right off the bat, this gives us the beginning of an algorithm for computing the SVD. Okay. So just leveraging what we already know how to do, what we could do is this. So go ahead and compute A transpose A. So just go ahead and carry out the multiplication. Now that's order n cubed operation, but we're going to be doing order n cubed work later anyway, so that's not a deal breaker. Then we use a symmetric QR algorithm that I summarized last time on C. And what that gives us is C, the symmetric QR algorithm gives us a sure decomposition of C, which is V lambda V transpose. So that's just the output of symmetric QR. What? Now, V is the V from the SVD. So we need three things: U, sigma, V transpose. So that gives us V. From lambda, we can get the singular values also just by taking square roots. But we also need U. So a better way to get U, which also gives us sigma, is actually an algorithm that I didn't cover, unfortunately. Well, I covered something very close to it. It is a QR factorization with column pivoting. Now, Gauss elimination with partial pivoting. In Gauss elimination and partial pivoting, you rearrange rows so that the largest element in a certain column was moved to the top. This is very similar that the QR factorization, you proceed like you would with QR normally, like using householder for reflections or givens or Graf-Schmidt, whatever. But as you perform those transformations, you also perform interchanges of the columns so that you take the largest column of the ones you have left and move it up front. Because otherwise, you might get columns in the middle that are 0, and that just throws off everything. It causes breakdown. So by always moving the largest column up to the front, that gives you a reliable algorithm. So, so factorization, what do you factorize? It's A times V. And the result of, well, okay, first, the form of a QR factorization of column pivoting is A times pi is equal to QR, where pi is a permutation matrix. That performs a rearrangement of a column. Just like when you have Gauss elimination and partial pivoting, you have PA equals LU. So P is a matrix that shuffles the rows of A. It's the same idea. Okay. So because it's multiplying on the right instead of the left, it's going to be permuting columns instead of rows. Just like how in PA equals LU, we're multiplying on the left to shuffle rows. So the QR factorization of column pivoting gives us U sigma. Now to relate U sigma to what we have here with the QR factorization of column pivoting, U is the Q that comes out of it. And sigma is the R times pi transpose. Now, so again, applying the shuffling of the columns. And the reason why we do this is because this permutation of the columns makes sure that the largest column is moved up to the front. So that ensures a proper ordering of singular values. Okay. Because we want to have sigma 1 first, sigma 2 second, and so forth, where sigma 1 is the largest. Also, R is technically upper triangular because it's a QR factorization where the second matrix is upper triangular. But we already know, theoretically, that AV, which happens to be U sigma, we actually are supposed to have a diagonal matrix here. So, so really, you're computing a factorization of an orthogonal matrix times a matrix that, while nominally it's upper triangular, but really it turns out to be diagonal, except for possibly some round-off error. So in fact, this particular QR factorization has very little work to do because it already has a form of a matrix that is orthogonal. It's just that the columns are misscaled. So all the QR factorization is doing is getting the multiples of these columns and putting them in here. And then the multiplication by this permutation matrix puts everything in the right order. All right, so this is one way of computing the singular value decomposition. Just this algorithm does the heavy lifting of computing the right singular vectors, and a relatively trivial QR factorization basically takes, you already have u times sigma, the QR factorization basically pulls them apart. So that we have u and sigma separately. Okay. Now, because the columns are already orthogonalized, we just need their lengths. And those are the lengths of the singular vectors. Okay, now, probably spent too much time on this algorithm as it is, for a simple reason that, like every first algorithm I've ever presented to you all semester long, it's a lousy algorithm. You know my routine. I give you my event like, hey, we're done, and then like, no, we're not. So, funny yank your chain. Now, why is this a lousy algorithm? Because of this step right here. There are certain cardinal sins in numerical linear algebra. One of them, from before, from AX equals B, is you never explicitly form the inverse. Even though our faculty here, Dr. Harris or Dr. Horner or whoever would have been, who teaches 326, has you guys spend weeks computing the inverse explicitly. And that's something you would never do in an application setting, which is why that class needs to be burned to the ground and rebuilt. Worse than Notre Dame. Oh, okay, that's all right. Okay, so too soon. Yeah. All right. But
that family
yeah, because of course that's where it's needed most, huh? Yeah. Anyhow, and this is another. We should not explicitly compute A transpose A. And the reason why is this causes a loss of information. So, in other words, not all of the digits in the entries of A are represented in the product, because when you multiply entries together and add them all up, there's some digits from entries of A that are going to be lost from truncation for round-off error. So we try to avoid working with A transpose A explicitly. Now, where have we seen A transpose A before? What other problem does that come up in? I know you're all thinking, oh, I know this, but long forgotten. From least squares. So I just put you out of your misery now. The normal equations. You solve a least squares problem by solving the normal equations. You have A transpose A. What?
Is any of this normal?
Well, it's all orthogonal, so it is normal in that sense. If you're solving A transpose A, X is equal to A transpose B. And so for that, you'd have to form A transpose A. And normal equations, already mentioned, is not a good method because A transpose A is badly conditioned. The condition number is a square of that of A. And that's why it's better to use a QR factorization which works only with A, not A transpose A. So for that problem as well, it's not a great idea. So how are we going to get around this? Because we know the singular values squared are the eigenvalues of this A transpose A. So is there a way that we can compute the eigenvalues of A transpose A without ever forming A transpose A? In other words, can we fake it? Because actually, that's really the theme of this whole chapter. It's literally fake it till you make it. So we're going to pretend to apply the symmetric QR algorithm to A transpose A without ever computing it. And get the singular values in a way that avoids that loss of information due to round off error. And we can do that by understanding how the symmetric QR algorithm works. And since I just covered that on Monday, and the unsymmetric QR algorithm the week before, so if we're going to compute the eigenvalues, what is the very first thing we do? We reduce A to what form at the beginning? Hessenberg, which in the symmetric case is also tridiagonal. So the symmetric QR, if we were to apply this to A transpose A, so we start with A transpose A, and then we carry out some. I need to check my notation here. All right. What?
That's supposed to be symmetric.
Yes. Symmetric QR applied to A transpose A. All right. So we apply some orthogonal transformation to A transpose A to reduce it to some tridiagonal matrix T. Where V1 is a product. Yes, my writing is already deteriorating. It's not a good sign, but we still have ways to go. This is a product of householder reflections, or as I lazily call them, householders, that zero out all the entries below the subdiagonal to make to give us our tridiagonal matrix. So here's what we'll do instead. Instead, the AD we'll still use householder transformations to obtain the following. So A times V1. So that part, AV1, I'm still going to compute. And then a different product of householders on the left to reduce A to a matrix B that has this structure. So it has D1, D2 on the diagonal. And, okay. I wonder if I'm making an assumption here about the size of A. Because we still have an m by n matrix. Okay. Well, I forget to say this in the book, but all right. So at this point, for simplicity, we're assuming that this matrix is square, and then we have entries above f1, f2, or at least I'm assuming that m is greater than or equal to n, in which case there might be some 0 rows down below. Again, just for description's sake. So this matrix, what do we call this? Where it's only the diagonal and one above. We call this upper bidiagonal. So it's also upper triangular, but we want to convey that there's only these two non-zero diagonals. And because of this structure, B transpose B, which I'll call capital T, is tridiagonal. So that's something that could be verified. If you have an upper bidiagonal matrix then you carry out the product, B transpose B, then it's tridiagonal. So, in other words, we're forming T implicitly. We're never going to explicitly compute it. We're just going to compute B, and then we'll work with it. Okay. Now, why does that actually work? Let me explain that really quick. Because this U1 here is not part of this at all. Okay. So, here's what we can do. So we start out A being some matrix, become VX's again. I'll make it 5 by 5. Actually, no, I'm going to make it 5 by 4. Okay. Saves me 20% of the paint. Now, what I'll do first is multiply on the left by some, actually I'll call it H1, a household reflection that's going to zero out all of the first column except the first entry. Kind of like QR factorization. Then, when I apply a household reflection on the right, I can use that to zero entries of a column. Sorry, instead of zeroing entries of a column, it's zeroing entries of a row. So, H1 transpose A, H1 tilde, so it's a different transformation, even different size. So for this one, I'm going to leave the first two entries alone, and then zero out these entries right here. We still have everything else. Okay. Now, so I need to explain why this is actually feasible. It's these last three columns, not the first column, are the only ones that are affected by H1 tilde. So now everything's kind of turned upside down, like or opposite of how we're accustomed to thinking of household. We think of household reflections as something that you apply on the left and it zeroes part of a column. Here I'm applying on the right, it's zero part of a row. But if I transpose everything, then you have it in the perspective you're accustomed to. But because really what I'm doing is I'm only interested in this part of the row, and coming up with like a V, like your household vector V, that's going to work on this. I'm ignoring this altogether. So, so H1 tilde is going to have this form. It's going to have a 1 here, and then it's going to have something else down in here. So this is the actual meat of it. So this would be identity minus V1, V1, 2V1, V1 transpose. So that's where the actual householdering is going on in this lower right n-1 by n-1 block. Everything else up here is identity. So that's why when I apply this to the right, it's not going to disturb the first column at all. So all that work I did to zero out these entries is preserved. Whereas if I tried to zero out this one also, I'd wreck this. So that's how this process unfolds. And then I'm going to apply another transformation on the left to get rid of these entries, and then another one on the right to get rid of these, and I'll just keep going until there's nothing left except those two diagonals. So that's how this process unfolds, working on all, in this case, n columns. So I have U1 transpose is equal to, well, starting with H1 transpose, H2 transpose, up to Hn transpose. And then V1 is equal to H1 tilde, H2 tilde, up to Hn tilde. So U1 and V1 are products of these household reflections that are meant to reduce A to this upward bidiagonal matrix B. Now, now, what you can also show, I won't go for the details here, but by the implicit Q theorem, this V1 is essentially equal to the same V1 I have over there. So in other words, if you went to the trouble of forming A transpose A and then carrying out the same old Hessenberger tridiagonal reduction to get this matrix T, this transformation and this transformation are essentially the same. In other words, you may have sign discrepancies, but that's it. And of course, round off error. We always have that. Okay. Because what you would do is you would show that this transformation and this one have the same first column, and then by the implicit Q theorem, that determines the tridiagonal reduction uniquely. So in this case, we're able to fake it. We're able to implicitly get T without ever forming A transpose A. So questions about what happened here?
In this last matrix right here, so there's supposed to be two diagonals of x's left. Are you done?
Oh, wait.
I saw you circled that right there. Is that supposed to be zeroed out? Okay.
Yeah, only that one.
Right.
Yeah.
Okay. That was.
Whoops.
Okay.
Yeah, so I guess there's not much to do with that matrix. Well, after that, I would continue over
Right.
here
Yeah. I
and
just was.
there, but that's it.
You had that one X circle. That was messing me up.
Yeah, so what that means, if you have a matrix that is rectangular like this one, some of these household reflections would actually be identity. There's nothing to a zero. So that makes things a little easier. Now, what we could do at this point is, now that we have B, we could form B transpose B equals T and then apply the rest of the symmetric QR algorithm to T. But again, loss of information. We're not going to do that. We want to try to do everything explicitly on B, not T. So again, this comes from understanding how the symmetric QR algorithm works to try to implicitly carry it out. So if we were to do symmetric QR, on T. We do the following. Take T, we select our shift, which in this case would be a Wilkinson shift because it's symmetric. We perform a QR factorization, and then update T by multiplying the factors in reverse order and adding the shift back in. Severe weather again.
Yes, again. Yeah, and then a lot of high schoolers in the area already canceled.
On Thursday.
Yeah.
Tomorrow. Okay. Well, let's see. Thursday afternoon or evening. Ugh. Yay.
It's supposed to be pretty bad up there.
Oh, what?
They said that some of the schools are letting out after a half day tomorrow in the afternoon.
Oh.
Schools.
Okay.
It's supposed to be that bad.
Oh, jeez.
Yeah, so that's all.
Okay. Well, I was really looking forward to tomorrow anyway, so.
Just that too.
Yeah. Well, I don't teach, so it might be a longer Easter weekend. Okay. Hopefully it's not for tornado cleanup, but okay. Now, but how is this process actually carried out? Really what happens is we form T minus mu identity, and then a bunch of Givens rotations row rotations, so we multiply on the left to get R. So Q is a product of all of those Givens rotations. And I said to let us know by 8 a.m. if there's going to be a cancellation or something.
That email means classrooms will be empty.
Yeah.
They're like early morning.
And then what we do, that's a comma, my boy. Then T tilde is going to be R times those same Givens rotations, but now applied on the right, column rotations, and then we add the shift back in. So really, if we can get those set product Givens rotations any other way, that'll be good enough. And what's most important here is T and T tilde are both tridiagonal. And that's what's really going to help us. So instead of forming all of T, which is B transpose B, here's what we do. We will compute just the first rotation, G1. And we do that from the first column of T minus mu identity. So we select the shift, and then we at least form a first column, which we can get from the entries of B. So, and that's only going to have two entries, two non-zero entries. So, so that'll be quite easy to do. And because the idea is G1 transpose times this first column, so really it's T minus mu identity times E1, so first column. And I have Y and Z just being those two non-zero entries that we have, is meant to be the column that is some non-zero number W and then zeros after that. So it's meant to zero that second entry. That's what a Givens rotation does, as we saw from QR factorization. So we go ahead and work that out. Which transformation would do that job? Next thing is we take that Givens rotation and we apply it not to T, but to B. Because what's happening is, from the following, T times G1 transpose, G2 transpose, etc., and then G1, G2, etc., equals T tilde, but this is equal to, all right, so I'll write this again, T is B transpose B, and we get G1 transpose, G2 transpose, Gn transpose, or Gn minus 1 rather, G1, G2, Gn minus 1, okay. So, notice G1 is multiplied with B on the right. So what we actually compute is called B1 is B, our upper diagonal form, times G1 on the right. It's a column rotation. Now, B is upper bidiagonal. So I'll write that out. Okay. Now G is some Givens rotation. Now, here we're rotating the first two rows, so we apply on the left. That means we're rotating the first two columns when we apply on the right. So we need to see what kind of structure B1 has. So we are rotating the first two columns. The rest of the columns will be left alone. So I'll just fill in the remaining columns. Okay, so if I rotate these columns, what that means is, dang it, each of these two columns is a linear combination of these two columns. So, which entries in these two columns could possibly be non-zero? What?
The first one.
The first one.
Oh, yeah, those can be non-zero. What else?
Two.
Yeah. The second entries, because this first column is a linear combination of itself and this column. So some of this is going to pollute here. So now we've lost upper bidiagonal form because we have this rogue entry there. So now we have to deal with that. So what do we do then? We use another Givens rotation to zero that out. So that means we need to, if we're going to rotate rows now, because we just rotated columns, we're we're going to rotate rows. We're going to rotate the first 2 rows. Okay. So now I have. Okay, so we're going to have H1, B, G1. It's like, oh, that's a weird abbreviation for Hattiesburg. Never thought about that until now. Now, so what BG1, wait, okay, so my row rotation, actually going to put transpose here. Okay. And then BG1 has structure from before, so I have 2, 3, and then okay. So now what I'm going to do is rotate the first 2 rows, and okay. So if I rotate the first 2 rows, again, which entries could possibly be non-zero?
First 2.
More.
With first 3.
First
on the
First
column.
3. Yeah. So you have 1, 2, 3, and because the first row is a combination of itself and the second row, so it causes, again, a little pollution there. Now, oh, wait a minute. This got zeroed. That's the goal.
Right.
But now we have this one. Oh, yeah. Like even more unusual. What? Okay. All right. So we got rid of one unwanted non-zero entry, and add another. So do this again. Now we're going to rotate columns 2 and 3. So we're going to call this H1 transpose B G1 G2. So now we form a second column rotation, and the first column will not be affected anymore because we're not touching it. We're only touching the second and third column. So now which entries can be non-zero in these columns? Like, well, this one will be zeroed out. So I'll fill it in right there. But what could still be non-zero? Like in the second column. First 3 entries, because this one could pollute that spot. And then we have these 2 entries. Yeah, so now that entry is an unwanted non-zero. Let's do this again. It's so much fun.
Just throw the whole thing out.
Right, we're close to the end, I promise. So now we're going to rotate the second and third rows to zero that one out. So I have x0. Well, hold on. Okay. So that's still 0. We have these down here. Too small. So now I rotate these rows with the explicit intent of zeroing that. So I'll fill in a 0 there. This is still 0 because nothing's happening to the. Well, here we have both zeros. So that's still going to be 0. But when I rotate these,
You're gonna have x, x, x.
yeah, the second row, because this goes up here. Okay.
We're standing in the hole, dumping the dirt back on us.
Yeah. So now this entry is out of line. Do you see how this is playing out?
Yes.
Yeah. So it's going, so it started here, went here, then here, then here. It's like it's being chased. And that's actually what happens. We will continue this process. Now we'll jump down here. Okay, we'll go down here, then here, then here, and then, oh, there's nowhere to go, falls out. We are literally chasing the unwanted non-zero entry out of a matrix.
Can you erase that random zero that's next to the line? It's not bothering me.
Yeah, I'm not sure how I got there, but yeah. So we keep applying these given rotations to restore the upper bidiagonal form of B, which therefore would restore the tridiagonal form of T, which is B transpose B. And once again, by the implicit Q theorem, this product of the Gibbons column rotations, G1, G2 up to Gn-1, is essentially equal to Q in T minus mu identity is equal to QR. So we are simulating the QR factorization of this matrix by these column rotations that we use to restore the upper bidiagonal form. And the reason we know that's true is because we can G1 is the G1 is the first transformation that makes up Q. Therefore, the two transformations, what I did here versus Q, they have the same first column. So they're essentially equal. So that's what, so the implicit Q theorem is very useful, allowing us to fake applying the symmetric QR algorithm to T, but only actually working on B. So we can just keep doing this, but since the goal is to reduce T to diagonal form, but we're not actually forming T, we're not working with it, how do we know when we're done? And fortunately, it's actually easy to figure that out. So B has this structure as D's on the diagonal, and then F's on the super diagonal. So I've deferred some of this to a Chapter 6 homework problem, but so it can show, and therefore you will show, or at least part of this, if any of these entries, the D's or the F's, if any such entry becomes zero, because at the beginning we're assuming a non-zero, the decoupling occurs in B transpose B. So in other words, so one of these entries being zero is equivalent to a subdiagonal entry of T being zero, which causes the eigenvalue problem to decouple, as I showed you last time. So that's what we can do. We can still work with B, doing this, applying these transformations, chasing non-zero entries out, and then once that chasing is done, we look at what we have left. And if one of these entries is zero, then we know we can work on a smaller portion of the matrix. It's easier if one of the F's is zero, because that leads to immediate decoupling in T, whereas if one of the D's is zero, it's more complicated, which I won't really get into, basically you have to do some extra givens rotations to cause that decoupling to occur. But the point is, it can be done. So really, that's all it takes is you just so you want this to converge to diagonal form where you only have d's, where all the f's are gone. And when that happens, B converges to sigma. So you've actually reduced A to the to a diagonal matrix sigma, and V. How do you get V? V is a product of all transformations that are applied on the right. So any household reflections you applied on the right, any givens, column rotations, well, you accumulate all of those as you go, and that will give you V. And U, same thing, but for the left. So you accumulate all of those transformations. So because really what's happening is U transpose AV is equal to sigma. That's really what you're carrying out. You're starting with A, and you're applying all these transformations on both sides to reduce it to orthogonal transformations to reduce A to diagonal form. And so you just accumulate whatever transformations you applied. You get V from the right, and then U transpose from the left. And that's the Golub-Kahan SVD algorithm. So yeah, so Golub didn't do it himself. William Kahan, who I believe is still alive, he's a retired professor at Berkeley, developed this algorithm way back then. So what I described as chasing out is known as a Golub-Kahan SVD step. So that was their brilliant idea, in using the implicit Q theorem to make this happen, and I come up with a first practical algorithm, not requiring forming A transpose A or B transpose B, to compute the SVD. Okay. Well, that's actually all I have. So now I've dispelled that mystique. So if we survive whatever's coming at us, then I'll see you again in a week and cover something completely different after I figure out what that is.